Welcome to Let's Get to the Marks. We're looking at a time of flight question. This is from the A-Level 2023 AQA Paper 1. So for chemistry, let's get into the question. It's question 9. This is a question about TOF, or time of flight mass spectrometry. Give the equation including state symbols for the formation of Sr plus ions from Sr atoms by electron impact. Okay, so looking at strontium here, and we're looking at electron impact. That means when the electrons smash into the atom and knock off other electrons, making it an ion. So a couple of things here. We want to show the atom in its atomic form, so no charge, being hit by an electron. We use the E minus symbol, and then we do the arrow showing it as an ion. An electron has been knocked off. Now, if an electron has been knocked off, it joins with the electron that hit it to form two electrons. So you've got a stream of electrons banging into these atoms and removing an electrons, and those electrons join the stream. Now, we don't forget the gaseous state symbols. So whenever you're doing mass spectrometry, the symbols are gaseous. And that doesn't matter whether it's electron impact or any other form of ionization. Electrospray would also be gaseous. Okay, let's check out 9.2. A sample of strontium is analyzed by TOF mass spectrometry. The sample is ionized by electron impact. The ions are accelerated to have a kinetic energy of 7.02 times 10 to the minus 20 joules. An ion takes 9.47 times 10 to the minus 4 seconds to travel along a 95 centimeter flight tube. That's going to be 0.95 meters. So we just make our immediate conversion there, because distance in equations is normally in meters. Kinetic energy is half times mass velocity squared, and that's where mass is in kilograms and velocity is in meters per second. Now we're going to need the speed calculation. Normally for these time of flight calculations, you'll need the speed equals distance over time as well. So once again, mass is going to be in kilograms, so that's going to be important. You'll probably need a conversion there, and speed is in meters per second. And that just reminds us the fact that speed is in meters per second, that we need to convert that distance from centimeters to meters. So if you're wondering why I converted that, that's the reason. We're going to need Avogadro's constant, and the actual calculation, or the problem we're being set, is to deduce the mass of one ion. No, not deduce the mass of an ion. That's important, actually. It's not to deduce the mass of an ion. That'd be a very small number. This is to deduce the AR, or the mass number of this ion. So there's a mistake we could have made there. And that's important because if it was electrospray, we'd need to add -1 from our final answer, but we don't here because it's electron impact. So we haven't added a proton and increased its mass. Okay, let's have a little butchers here. What we're going to do is distance, which is 0.95 meters over the time, which we're told up here, underlined in pink, is 9.47 times 10 to the minus 4. And that's going to give us the speed. Okay, so that's going to give us the speed of the ions traveling along the tube, along the 1 meter tube. And so we write our speed out here, and that's in meters per second. And speed is interchangeable with velocity in this. I know velocity is a vector quantity and all that business, but essentially it's interchangeable with speed. So we're going to take our speed or velocity across, and we're going to whack it into the k equals half times mv squared equation. Now we want to get rid of the half m, so we times both sides by 2, which gives us 2 times the kinetic energy. And then we want to isolate the m on its own, so we're going to divide that by the velocity squared, which we've got here, and that's going to give us our mass, which is what we're going to need if we're going to work out the mass number. So what do we need to do here? We need to do 2 times the kinetic energy, and we've been given that above. I've underlined it in pink. It's the first thing underlined in pink. 7.02 times 10 to the minus 20 joules. So we're going to go 2 times 7.02 times 10 to the minus 20 joules. Oh my gosh, it's early in the morning. And then we're going to divide that by the velocity squared. Velocity is the same as our speed here. So we're going to divide that by 0.03.167899, which we're going to square. Don't forget to bracket everything in these equations, otherwise it comes out wrong. So, oh gosh, I'm using a combination of handwritten and type. That's never a good thing. But don't forget to bracket everything in your calculator. And you don't really have to type out all these long, dirty numbers, because you can just keep it straight into your scientific calculator. You just need to make sure you're writing the working out as you go in case you make a mistake. So just make sure you're writing the working out, keep your scientific calculator on the side, you're keeping the numbers in it all the way till the answer. Okay, now my answer that I've got is 3.95. You might get 3.96, depending on what you've put in, times 10 to the minus 25. Now that's the mass, and that's going to be in kilograms. And they reminded that, I've underlined it in pink over there, where M equals mass in kilograms. Okay, but we are looking at the AR, or the mass number of this ion. And in the periodic table, what is the mass number? It's the mass in grams of 1 mole of a substance. So we're looking at the AR in grams here. Okay, so we're looking at the mass of an ion or atom when you have 1 mole. So I need to times by 1,000 to get it into grams. So I'm going to do 1.395 times 10 to the minus 25 times 1,000, and that's going to give me 1.395 times 10 to the minus 22. That's 1.395. I've written 2, but I can't bother to cross it out. So there we go. Make sure you put a 3 there. And then, that's going to pick you up some marks, lovely marks all over the place here. What do we need to do next? Well, we've got the mass of 1 ion, but we need the mass of a mole of ions. Guess what? We've been given Avogadro's constant that you can call L. And that's 6.022 times 10 to the 23. So we want to, if we want to find out the mass of 1 mole of these ions, which is the mass number, we're going to times it by 6.022 times 10 to the 23. And that's going to give us a whole mole of the ions, which is going to be equivalent to the mass number. And if we pop that in the calculator, I think, I've got 83.987 on my calculation. Now, it doesn't say, but you'd normally round this to 1 decimal place. So 83.987, well, let's round that actually up to 84 because our mass numbers are generally going to be whole numbers. And so we'll round that up to 84 to calculate the mass number of that ion. Super, I've circled it here. All right, nice one. Let's move on.
Keep moving on, keep moving on, keep moving on, keep moving on.
So what have we got here? We've got 9.3. Explain how ions are detected in the TOF, time of flight, mass spectrometer. State how the relative abundance of the ions is determined, how the ions are detected, how the relative abundance is determined. Okay, so first of all, how are the ions detected? Well, after electron impact or electrospray ionization, they're going to be positive, these ions. Now, as they move towards the detector plate has electrons running through it. And those electrons are negative. So as the ions get close, those electrons are going to be attracted and they're going to zap out of the plate towards the positive ion, forming a current when it gets close enough. So if you connect an ammeter to the detector plate, you'll get a reading on your ammeter to show that ions are arriving. Now, how do we know what the abundance, how much of the ions have arrived? Well, we look at the size of the current, and that gives you, basically the size of the current is equivalent to the abundance of the particular ion. So if one particular ion arrives and you get 2 amps, and then another ion arrives, you get 4 amps, you know the second ion, there was double the abundance because it generated double the movement of electrons, or double the current. Coolio. 9.4. So let's make a little space for 9.4 and scroll down. We have, let's get this in properly. Just adjust a little bit so I've got all the space for the working out. A sample of strontium contains 3 isotopes, SR86, SR87, and SR88. So 3 different isotopes. 82% of the sample is strontium-88. The other 2 isotopes are in a 1:2 ratio of 86 to 87. Calculate the percentage abundance of strontium-87 in this sample. It's going to get us 1 mark. Use your answer to deduce the relative atomic mass, the AR, of the sample. Give your answer to 1 decimal place. So there's another 2 marks there. So first of all, strontium-88 has 82%, but we've also got strontium-87 and 86. So we know if strontium-88 is 82%, then we know that 87 and 86 must be equal to 100 minus 82. Basically, they've got to make up the other 18%, right? If we add strontium-86 and 87 together, they've got to equal 18%. But we know they're in a 1:2 ratio. So let's divide 18 by 3. You get 6, and divide that up into 1 and 2. So you get 6 and 12. So strontium-86 is 6%, and strontium-87 is 12%. So you got your first mark here because you've worked out the abundance of strontium-87, which is 12%. So we've just scored that first mark. Let's go to the next bit. Deduce the relative atomic mass, the AR, of the sample and give your answer to 1 decimal place. They're obviously the other 2 marks. So working out the AR and then rounding it to 1 decimal place is going to be the 3rd mark. So what we're going to do here is just what you do for any normal AR. You're going to do the abundance times the mass number of each isotope, add that all together to get the sum, divide it by 100, and voila. So 88 times 82 plus 87 times 12 plus we want 86 times 6. Oh, let me just write our abundance is 12% there for 87 in the right place. There we go. Well, that was the first mark we needed. So now we're going to do 86, just squeezing it in here around these 3 marks, times 6, and we want to divide that all by 100. That is going to give us our final answer of 87.76. And then we round that down here, as it says, round to 1 decimal place. You'll lose a mark if you don't, and you get 87.8. So you're going to get 1 mark for working out the abundance is 12% of strontium-87, 1 mark for the 87.76, carrying out the AR calculation, and then 1 mark for rounding to 87.8. Beautiful. 3 marks. Let's move on to the final part of this question. Let's go. Okay, so this last question to this, 9.5, electrospray ionization is used instead of electron impact for the ionization of a protein in a mass spectrometry experiment. Suggest why. So these suggest ones can always be quite difficult for some people, but think about it. Electrospray ionization is used instead of impact. What's the general difference here? When you use electrospray ionization, you add a proton in order to create the positive charge, so it will be attracted at the detector plate. With electron impact, you smash off an electron using a beam of electrons. The problem with electron impact, if you're doing a protein, what's a protein made of? It's made of amino acids. So I'm doing a real crusty G-level GCSE art, gangster level GCSE art drawing here. This is my protein, and it's being snapped here by the beam of electrons into fragments. Now, if you're trying to analyze the protein and work out its mass number, you might not want it to be fragmented. You might want to keep your protein whole and not be broken into pieces. So electrospray ionization would not be the best method. Sorry, electrospray ionization would be the best method because it avoids fragmentation of the protein, avoids it being snapped or broken into small pieces, whereas electron impact will do that. Okay, awesome. That's the final mark for this question. So, hope you enjoyed. Hit the like, subscribe, share. Yeah, let's get to the marks.
You're still here? It's over.